This example will demonstrate the steps required to create an external superelement using Femap version 10 and NX Nastran version 8.1. An external superelement is a stiffness and mass matrix representation of a finite element model. It is normally created by reducing a large detailed finite element model to a reduced stiffness and mass matrix at a limited set of user-selected boundary nodes. This reduced model can then be used as a component in a system-level analysis. The proper selection of boundary nodes combined with the use of modal reduction techniques can create a very efficient way to accurately represent the static and dynamic behavior of a structural component. This video will demonstrate the steps to create an external superelement and then included it in a system-level analysis. First we must identify the boundary nodes for the external superelement. In Femap, this is accomplished by creating a constraint set. Now we actually select the boundary nodes. In this example we are selecting a group of nodes that was previously defined. We have selected the nodes that attach this component to the remainder of the vehicle. We select the fixed button which checks all 6 degrees of freedom. The next step is to create an analysis. A static or normal mode solution can be used to create the external superelement. If you intend to use modal reduction, then be sure to choose a normal mode solution. Now create a new analysis. Now we will edit the boundary condition form to select the boundary nodes for the A set. Set the constraints to none since we want the component to be free. Now select our boundary node set for the A set. Now, add the Nastran command to create the external superelement by editing the case control. We will manually type in the command to the start text window. See the NX Nastran documentation for details on the command syntax and options. In this example we are using the OP2 format, so we will create the Nastran assign statements which will allocate the files where the matrix data will be written. We will edit the executive and solution control form and type in the assign statement to the start text window. The unit number on the assigned statement must match the unit number on the extscout command. We can now preview the Nastran input file. Here we see the case control command that will create the OP2 style external superelement, and the matching assigned statement can be seen at the top of the file. If we scroll down into the bulk data, we see the A set bulk data entries that define the boundary nodes. Now we will show the steps to create a system analysis using an external superelement. First, we will create a new normal modes analysis. Now we will edit the executive solution options. Here in the System Cell field, we will input the parameter to set the tolerance used by Nastran for duplicate nodes. This is required because our attachment nodes exist in both the residual model and external superelement. Next we use the Start text window to type in the assigned statements required to attach the external superelement files. The assigned statements should use the same unit numbers as the creation run, since this data is also stored in the ASM file that we will use. Now we will edit the bulk data options form. Here we select a previously defined group which represents only the residual structure. Now we select the End Text button. We type in the include statements that point to the ASM files from the external creation run. The ASM file contains the information used by Nastran to attach the external superelement to the residual structure. Not we will preview the Nastran input file. The assigned statements attach the files that contain the external superelement matrix data. If we scroll to the end of the file, we see the include statements. These files contain the data needed to attach the external superelement to the residual structure. Now let's review some results. We will compare the results of the full system model without superelements to the results using external superelements for the two boosters. The model on the left is the full system model and the one on the right is the model using two external superelements for the boosters. The superelement model consists of the residual, superelement 10 and superelement 20. Notice the difference in the answers. The superelement model has a higher frequency, and notice the mode shape of the boosters. The boosters do not exhibit the shell mode that is seen in the full model. This is caused by using only a static reduction and also not picking enough boundary nodes to represent the shell mode. We can correct this by selecting more boundary nodes in the external creation run, or a more efficient method is to use the Craig-Banton modal reduction technique. There are 3 steps to create the additional input required to make the external superelement a Craig-Banton style model. The first step is to create Nastran S-points to act as placeholders for the modes that we calculate. We create one S-point for each mode we want to retain. The number of modes might be a function of the frequency range of interest, or it could be the number of modes needed to include the mode shapes of interest. The second step is to create a new Femap constraint set and place the S-points in the set. The third step is to modify the external superelement creation run and select this new constraint set as the Q set. First create the S-points using the Model Node menu. Select the parameter to set the type to scalar point. Type in the ID number of the first S-point, then click OK. Repeat this for the number of S-points required. Now we will create a new constraint set for the Q set points. Create the nodal constraints by selecting the S-points we just created. Edit the external superelement creation run. Select the QSet constraint set before submitting the creation run. Make sure that there is one S point for every mode that is calculated in this run. Now we can see that the addition of the Craig-Bampton modes to the external superelements has greatly improved the accuracy of our dynamic system model.